Let's discuss the heat transfer through hollow cylinder. So in this we'll discuss two different cases. First one, where cylinder is made of single material or single layer of the cylinder is there, and second case where cylinder is made of multiple layer or multiple material. Okay, so let's start with the first case. So in this one, assume this is R1 is the inner radius and R2 is the outer radius of this cylinder. Inside wall temperature of cylinder is T1 and outside wall temperature is T2. Length of cylinder is L and the thermal conductivity is K. So we know the equation, Fourier's equation for heat transfer is Q is equal to minus Ka dt by dx, and this is the equation used for a heat transfer through plane wall, and this is a case of hollow cylinder, so we need to change this equation, and a new equation will be Q is equal to minus Ka dt by dr, because in this case as we are changing the radius, temperature will change, and this heat transfer is inner side to outer side. That means T1 is greater than T2. So this is the equation where as we are changing the cross section, as we are changing the radius, so cross section area will also change. So, and this equation represent a very thin layer of the cylinder. This is a very thin layer having radius of r, and thickness of this particular thin layer is delta r, and temperature difference between this layer is delta T. So if radius is r, and so cross section area is A is equal to 2 pi r into L. So let's again rewrite this equation. Q is equal to minus K 2 pi r L dt by dr. As I already told you that with respect to change in a radius, temperature will change, so we need to integrate this equation with respect to limit r varies from r1 to r2 and t varies from t1 to t2. So now integrate it. So for integrating, I am rearranging the equation. So dr by r is equal to minus k 2 pi L by Q, and this is dt, T1 to T2, and this is R1 to R2. So after integrating, we'll get ln R2 by R1 is equal to minus 2 pi L K by Q T2 minus T1. Okay, so this is the final equation. Q is equal to 2 pi KL T1 minus T2 by ln R2 by R1. So this is the equation for heat transfer through a cylinder made of a single material. And if cylinder is made of multiple layers or multiple material, so this is the second case. So in this one more layer is there. So now suppose this is the radius, inside it is r1, this one is r2, and this radius is r3. Okay, inside wall temperature is T1, and this wall outside temperature is T2, and this wall outside temperature is T3. This material having thermal conductivity K1, this one having K2, and again length is L. So as we have already derived one equation, so again in this case, if I want to write an equation for a cylinder having thermal conductivity K1, so now equation is same, this equation. So I'm rearranging this equation again in the form temperature T1 minus T2 is equal to Q dot ln R2 by R1 by 2 pi KL. This is equation number 1. Similarly, we can write the equation for material having thermal conductivity K2. So now this is T2 minus T3 is equal to Q dot ln R3 by R2 by 2 pi. This is a K1, okay, in this case. So this is K2L. This is equation number 2. So if you want to get the equation for composite layer, in that case you need to add these two equations. So this 2 will cancel. T1 minus T3 is equal to Q by 2 pi L common, then ln R2 by R1 by K1 plus ln R3 by R2 by K2, and again we are rearranging it. So now final equation is Q is equal to 2 pi L T1 minus T3 divided by ln R2 by R1 by K1 plus ln R3 by R2 by K2. And suppose if this cylinder is made of n number of layer, in that case this equation will extend and the ln R n plus 1 by Rn by Kn. This is the final equation for composite cylinder for n number of layers.